Yeah. Okay.
Okay, let's go ahead and get started today's lecture. A few announcements before we begin. The goal for today's lecture is to continue our discussion about fluid kinematics. Last time we had talked about deformation as being one type of motion, deformation and rotation being the two types of relative motions that two material points that are in a fluid field can experience. And so we talked about them a little bit. We did some derivations, um, and we arrived at a certain relationship, a certain equation, which I will revisit in terms of just providing some background. And then we'll continue a discussion about deformation, specifically looking at how we might be able to evaluate the viscous stress tensor tau, the capital tau that we had talked about last time. And I'll talk a little bit about that. And then the goal is to arrive at the Navier-Stokes equation, which is the constitutive equation in which the viscous stress tensor has been evaluated for a Newtonian fluid. And then what we'll go ahead and do is do some problems. Do one problem, the planar Poiseuille flow, which is one of the classic fluid dynamic problems, essentially the flow between two parallel plates. The goal for that example is hopefully for some of you to make a connection between what you might have seen before in undergrad and where we'll or where we'll get to in this lecture, and then we'll continue down that path. I'll see how far we can get today in terms of the just talking about the planar Poiseuille flow, and then subsequently talking a little bit about forces and buoyancy and so forth. As I mentioned, the problem set one, I expect to be able to post it later this evening. So you'll see it on Canvas. I'll send out an announcement once it has been posted. As I mentioned, last lecture, it'll cover material through Tuesday's lecture next week. However, you should be able to start attempting at least the first couple of problems. So I would encourage you to do so and not wait until next weekend to attempt the problem set, and make use of office hours next week to ask questions if you have any about the homework. It's a relatively straightforward homework. There aren't any difficult problems per se. However, we are available, the T and myself, we are available to answer your questions if you have any. Quiz 2 will be posted at 5 p.m. Today, and it'll be due just before midnight tomorrow. So please, as you had for quiz 1, attempt the quiz when you're ready, when you've reviewed all of the material from lecture this week, so both Tuesday's lecture as well as today's lecture, and then attempt the problem when you have when you're confident and are able to do so. Okay, so just to recap a little bit about in terms of what we had, where we had left off last time. We were talking about the two types of deformation, the two types of deformations that a material point can experience. The first one being dilation, in which we have this box here that increases in terms of its size. So you have an increase in volume without a change in shape. So you have a volume change with the same shape. Or you could have shear, and in a shear-based motion, there is a shape change without a change in volume. And then what we had done was talk about how dilation can be represented mathematically, right? Basically by using the equation of continuity, which falls out of the mass balance equation. So let's cover that once more. So let's talk about dilation. We had defined the specific volume as being 1 over rho. This is again the volume per unit mass, so it's the inverse of density. And if we were to plug in V hat into the general equation of continuity, which is d rho dt equals negative grad rho v. So if we plug in V hat for rho, again, I'm not going to use the chain rule and use every single step in calculus to arrive at this equation. You're free to try it out on your own if you are interested in, but the important thing is the identity that you get is a dv hat 1 over v hat equals dv hat 1 over v hat dv hat dt equals grad dot v. Again, v hat is the specific volume, small v is the velocity. And so here what we have is, on the left-hand side, the rate of dilation. Is equal to the divergence of velocity. And so if we have a situation in which there's uniform expansion in that it's equal in all directions, we can typically describe that in terms of spherical coordinates.
The previous slide. Is that tau or d for specific one?
This is dv dt. Just dv hat dt. Okay, and so if we have uniform expansion, the way that I've drawn it a couple slides ago, in that there's no preferred direction. We can describe this in terms of spherical coordinates. And in spherical coordinates, v would typically be a function of r, which is the distance from the center of the distance from the origin, essentially, and t in general. And so if you were to look in the text, the equation, so del dot v, so again, the divergence of velocity, del dot v, the textbook has a table that provides the divergence of velocity in terms of rectangular coordinates, cylindrical coordinates, and spherical coordinates. And so I'm going to just say from text, chapter 6. I don't have the exact table in front of me, but I'll look into providing you with the exact table where this is. But if you look at chapter 6, early on, there's a table that has del dot v, and in terms of spherical coordinates, this is 1 over r squared ddr, r squared vr, which is some function of time. Then what we can go ahead and do is to evaluate VR essentially by moving r squared over and then integrating with respect to r and then dividing with respect to or rather taking r squared over, using the chain rule to expand out the term that's in the bracket on the left hand side. And then when you do those steps, what you end up with is VR RT is r over 3 f t. So expand and simplify. And this is, we define this as being the divergence of velocity, right? And so what we have is that VR r comma t equals r over 3 t, which is equal to r over 3 del dot v. And so going back to the, let's see, let me just go back a few slides here. Going back several slides. Ah, right there. Just looking at this term here, 1 over delta r, d delta r dt. If instead we considered a velocity field like so, in which we still have the same two material points, 1 and 2, except that now we consider 1 to also be the origin. right? If this is the origin, then basically this is R. There's no delta R, right? Because delta R implies that 1 and 2 are points that are distinct from the origin. But if 1 is the origin, then the distance between 1 and 2 is simply R. And so that equation that I just pulled up, rather than write it as delta R, we can just simply write it as R. So 1 over R dr dt is 1/3 del dot v. Okay, so far we've considered purely dilational deformation. Yes.
Oh, so do you assume that Y is also moving, like the origin is also moving?
So if 1 is the origin, right, it's fixed. 2 is the only material point that's moving. So R is always going to be the distance between 1 and 2.
Makes sense.
So it's a little bit abstract. Again, this is just to simplify, and you'll see in a second why we've simplified it a little bit. Basically, just imagine 1 to be now fixed and 2 to be the only material point that's moving. And so that allows us to just remove the delta, and it simplifies the notations a little bit. So, okay, so we have this equation here, 1 over R dr dt equals 1 over R del dot V. Again, this is for a dilational deformation.
So on the right side, when did R go right? So it's just 1/3 instead of R over 3.
Right, so, excuse me. I just moved R over here. So just moved it over to the left-hand side. Okay, so let me just rewrite that equation that we had before with the deltas. Maybe if we just simplify it a little bit. So we had 1 over delta R, d delta R dt equals P dot how dot P, right? This is the most general form. And if it's purely dilational motion, and we have 1 over R, the way that we had written it before, dr dt equals 1/3 del dot V. But what we'd like to know, and this is the more mathematically challenging, to a certain extent, the more mathematically challenging expression is we want to know what the stress term is, right? So the deformation, the stress deformation term is. Rather than derive it from first principles, which is actually exceedingly difficult and challenging to say in the least. What we'll do is simply subtract these two. So we'll subtract equation 1, or we'll subtract equation 2 from equation 1. So again, just keep in mind this capital tau term contains both the dilation and stress terms. We arrived at an expression for the stress term. Yes. Oh, excuse me. We arrived at an expression for the dilation term. We can subtract the two to get an expression for the stress term. Yes.
Could you remember what P stands for?
We had defined it last lecture. So P is P is delta R over capital delta. It's a unit vector that has magnitude 1. That's defined by the position vectors. Okay, and so if we were to subtract these two, equation 2 from equation 1, we would end up with what is the shape-changing deformation term, which is also called shear stress. Subtract 2 from 1. And so what we're left with when we do that is 1 over delta R d delta R dE equals P. We still have this capital tau term minus 1/3 del dot V delta. Just keep in mind this is a tensor, so we need to associate it with a unit tensor dot P. Okay, so we have now a form of an equation, right, in which we have an expression for the two important deformation terms, dilation and the shear stress term. I'd mentioned a couple of lectures ago, or last lecture, that the dilation term does not really contribute a whole lot to tau, and we'll see why in a second. Before we move on, I just want to mention that for now we're going to skip the discussion about rigid body rotation. And I will mention here that the strain function does not depend on omega. So we'll come back to the omega term probably in a few lectures when we talk a little bit about vorticity, but for now it's not important. But we have this term here. It's rather difficult to use, right? It has a bunch of tensors in there, a bunch of dot products. It's still here on the left-hand side. It is still the rate of deformation, or the rate of strain, right? And so we still need this to be in a form that's useful for us to be able to arrive at an empirical form for tau, small tau. And just as a reminder, the equation that we're dealing with so far, the equation of viscous stress tensor is rho capital dV dt equals negative grad script P. plus L dot tau. And so it turns out that this particular form, this is as far as we can get to mathematically. What people have done over the past 100 years or so is to reduce this mathematical form that we have into a form that's more useful in terms of relating small tau to capital tau using the following empirical correlation. And so, empirical correlations, these are based on observations, specifically experimental observations. And what people have found is that for Newtonian fluids, Newtonian fluids have characteristic constant density, constant viscosity, water being one example. So it doesn't depend on the deformation of the fluid. That they found that tau has a empirical correlation. So again, this is not something that can be mathematically derived, but empirically it looks like so. So the first term in the bracket, this is the same as that we just derived. So this is the term that contains the shear stress. Right. And I mentioned there's another term. I'll talk about what mu and kappa are in a second. So this is mu, this is kappa. So 3 kappa, 1/3 L dot V delta. So the term that's in the first bracket, this is the term that is a consequence of shear stress. The second term here is the consequence of dilation. And as it turns out, one thing I should just clarify here, this is Newtonian fluids, or, and we'll talk about this in a second, or generalized Newtonian fluids. So generalized Newtonian fluids actually have a change in viscosity as a consequence of shear stress. Newtonian fluids don't, but both generally follow this empirical correlation. Yes?
Is there any usefulness in the equation we solved before if we're just going to end up using if we're just going to end up using empirical correlation?
Yes, there is, because we use this term is the same as this term here.
So like a fitting function?
Well, this is where you can, this is the best that we can do mathematically, as I mentioned. Empirically, they've gone ahead and introduced these two factors, mu and kappa, which enable you to now use this equation, so that relate tau to the dilational and the shear stresses. So you still need to understand where this term in the bracket comes from, which is why we covered it. But the mu and kappa terms are something that is a consequence of experimental observations. Yes?
Could you repeat again for generalized Newtonian fluids? Mu is a function of what?
Mu is a function of the shear. stress, right? So I'll cover it in a second. So mu is constant for Newtonian. For generalized Newtonian, mu is non-constant. For now, that should that's let's work with that definition. Specifically, how mu depends on tau, we'll talk about in a second. So a few things here. One is that mu is the shear viscosity. And as I mentioned, this may or may not be constant. So for Newtonian, it's constant. For generalized Newtonian, it's generally not constant. But we'll see there's the generalized Newtonian fluid. For example, paint is a generalized Newtonian fluid. We'll cover that as an example. And it has a unique property in that the viscosity is very high, except if you apply a certain amount of stress. Beyond a certain amount of stress, the paint starts flowing. But if you don't apply the stress, the paint doesn't move. And so there's what is known as a threshold in terms of the amount of force that's required to make paint flow. So it's a little bit more complex than a Newtonian fluid. As I mentioned, we'll talk a little bit about that later on. But for now, mu for Newtonian, it's constant. For generalized Newtonian, it's not constant. Kappa, on the other hand, is a term that is the dilational viscosity. And to a reasonable approximation, kappa can be neglected. It can be considered vanishingly small. And the reason for that is, again, these are experiments from experiments. People have determined that the dilational viscosity is significantly smaller in terms of its magnitude than the shear viscosity. The other, so if kappa is vanishingly small, essentially the term that we have, the dilational, the term that contributes to the stress tensor, the dilational component that contributes to the stress tensor can be neglected, right? Because the coefficient is essentially 0, vanishingly small. And the other simplification that we can make is that for constant density fluids, as I mentioned, so one thing I should also mention here, whether the fluid is Newtonian or generalized Newtonian, rho is constant for both. So for constant rho, the additional simplification that we can make is that the equation of continuity reduces to 0. Right, so we've made, this is a simplification. This is another simplification. So going back to this equation here, this term here can be neglected for constant density fluids, and kappa is vanishingly small, right? And so the only terms that survive after making these simplifying assumptions, which for this class are all valid, is that we now have an expression for tau, which is equal to 2 mu capital tau. so again, just as a reminder here, tau is the stress tensor. Mu may or may not be constant. And capital, or yeah, this is the rate of strain tensor. Right, so this is how stress is related to strain. Or let me just rewrite T tau equals 2 mu. Yes.
Professor, could you explain really quick how constant density makes the divergence 0?
So d rho dt equals negative grad dot v.
Right.
And so this goes to 0. Well, this is constant. And so del dot v equals 0.
Gotcha. Thank you.
Right, so now we have an expression. So here's how stress is related to strain for a fluid. And actually, this is a fairly important, very important identity, I would say, in fluid mechanics. And so certainly for this class, but in general, this is usually the starting point for solving most fluid dynamic problems that are either Newtonian or generalized Newtonian that have constant density. And this is, as I mentioned for this class, it's important. If you start getting to situations where you have variable density and so forth, at that point, you start needing to apply various types of computational methods beyond the scope of this class. But analytically, you can solve most problems that you would encounter in fluid mechanics with this relationship. Okay, so this is great. We have an expression now in terms of for stress in terms of strain. The other thing that we know from our discussion in the previous lecture is that the strain tensor here, rate of strain tensor, is by definition grad V plus grad V transpose. Right, we'd split that dyad grad V into the symmetric and anti-symmetric tensor. This is the symmetric strain rate of strain tensor. So by definition, this is what the value is. And so we can use this. We can simply plug in this expression into this equation here. So what we have is the shear stress equals mu grad V, which is the dyad, plus grad V transpose. And so here I would refer you to tables 6.4 through 6.6, which in the second edition of the text, first edition will probably be 5.4 through 5.6, which essentially gives you the expression for the term in the bracket here. And once you have that, what you can do is to plug it into the Cauchy momentum equation. So that you have an expression for tau. And then you're able to solve various types of problems. Okay. Um, so just going back a few slides here, the equation that we have is rho dv dt equals negative grad script p plus del dot tau, right? And so what we need is not just an expression for tau, which we now have in terms of the velocity field, but an expression for del dot tau. And so here's where the constant viscosity assumption will come into play. So what we're going to do is now take the divergence of both the left-hand side and right-hand side of this equation. So we're going to multiply tau, or not multiply, but take the dot product of del dot tau and on the right-hand side, we'll have del dot this entire term that's on the right-hand side. And so when you do that, so let's do that. So we have del dot tau equals del dot mu grad v plus grad v transpose. Now the only way you can pull out mu is if it's constant. If mu is not constant, then you can't pull it out. So we're going to assume here, we write that in different color. So assume constant mu. Again, this is for Newtonian only. So we're going to be able to pull out mu. And when we do that, we now have del dot tau equals mu grad square v, or del squared, or constant viscosity. Yes, constant viscosity. So it's I've skipped again a few mathematical steps here. As I said, it's not important in terms of going from this step to here, the specific steps, but the end product here, the identity is important. And so what we can do is plug this into the Cauchy momentum equation, and what we have is a very important relationship between the total material derivative and the dynamic pressure field and the velocity field, which is, as hopefully some of you might recognize, the Navier-Stokes equation. This is, again, for constant density, viscosity, Newtonian fluids. So this is going to be the starting point for most of the problems that we solve in this class. One thing I'll mention is that for this particular part of the class, we will consider generalized Newtonian fluids and probably a little bit later on as well. But as we start getting into more, for example, when we start considering Stokes flow, lubrication approximation, and so forth, we'll primarily focus on Newtonian fluids. I might throw in an example or a problem here and there that involves generalized Newtonian fluids, but you won't be expected. Again, it won't be math heavy, relatively straightforward in terms of being able to solve for velocity fields and so forth. We'll also later on in this course consider order of magnitude analysis. And so, for example, you might be asked to, rather than solve a generalized Newtonian fluid, solve the Cauchy momentum equation, which sometimes can be nonlinear because you start introducing dependence of viscosity on the shear stress, that rather than solve the entire equation is to make certain simplifications. So we'll go through some of those examples, but this is going to be the primary governing equation that we solve or that we use in this class. And this is sort of where I wanted to arrive. And so all of the math that we did in this lecture and previous lectures, again, was intended to arrive at this identity here. A few notes. One is that the term here is the term that represents the viscous forces. And the left-hand side, as before, if you notice, we haven't really worked a whole lot on the left-hand side. Left-hand side is essentially a conversion of mass times acceleration, right? And so this is the inertial term, represents inertial forces. And there's inherent nonlinearity in the left-hand side. And so we'll primarily focus on viscous forces for now and look at how we might be able to solve problems. And then later on, we'll bring in inertial forces. Okay, so let me just recap the key concepts here in terms of what you should focus on and how we arrived at where we were. So rho dv dt equals negative grad script p plus del dot tau. Again, this is script p contains both the gravitational term as well as the pressure gradient. Okay, so this is, again, the dynamic pressure. This is, again, the viscous stress tensor. Viscous stress tensor contains both the shear term, the shear force term, or rather the shear stress term, as well as the stress as a consequence of dilational deformation. But as we saw previously, that experimentally, people have determined that kappa, which is the dilational viscosity, is vanishingly small, and so we can essentially neglect the dilational term and focus simply on the viscous contribution. And what we arrived at is that tau equals 2 mu tau, again relating stress and strain. This by definition is 1/2 del V plus del V transpose. And so when we plug all of these factors in and take the divergence of the viscous stress tensor, we get u grad squared V for Newtonian fluids. which leads to the Navier-Stokes equation. And I've just expanded out script P here. This is same as negative grad script P. Okay. So then, okay, so this is the Navier-Stokes. Let me just write that again. So then the remaining question is, what about generalized Newtonian fluids, the ones that have variable mu, that don't have constant viscosity, constant field viscosity? So what about fluids with variable mu? So these are, as I mentioned, generalized Newtonian fluids. Importantly, they still have constant density. And so for generalized Newtonian fluids, mu is not constant, but mu is a function of the rate of strain tensor. And what we have is table 610 in the text. It gives you what the rate of strain tensor is in terms of the velocity field. So it gives you the value for 2 times the rate of strain tensor squared. And this ends up being useful. The form that it's provided to us, it's useful for solving Cauchy momentum equation. We'll go through a few examples, so hopefully be a little bit more clear. Let me just also put it this way. There are various models. That allow you to represent mu as a function of the rate of strain tensor. And table 610 gives you what the rate of strain tensor is And so what you can do is plug in the rate of strain tensor terms of the velocity field into the expression, the relationship that is given to you that describes mu as a function of the rate of strain tensor. Let's look at a few of those models and see how that is possible. The first one that we'll cover is known as the Carew model. This is a model that is typically used for polymeric liquids. I think some of you working with polymers or polymeric liquids would encounter polymer solutions, so forth. The polymer solutions, if they're very dilute, can be reasonably approximated to be water and modeled as a Newtonian fluid. However, this particular model is typically for very dense polymer solutions, so things that require polymer processing, typically in manufacturing and so forth. And so what ends up happening with polymeric liquids, specifically dense polymeric liquids, is that mu is constant at low shear rates. However, when you bump up the shear rate, so at high shear rates, and I'll talk about what constitutes low versus high in a second, but at low shear rates, mu is constant, behaves like a Newtonian fluid. But at high shear rate, mu actually decreases as some power of the rate of strain tensor at high shear rates. And so what the model is, the relationship between the viscosity, the shear viscosity, and the rate of strain tensor is given empirically again as mu minus mu infinity over mu naught minus mu infinity equals 1 plus 2 lambda tau squared n minus 1 over 2. And here, mu infinity, mu naught, lambda, and n are constant. They're given constants for a fluid. And usually the value for n ranges from 0.2 to 0.6 for polymeric liquids. So what if the value for n was equal to 1? What would happen to this equation?
It would equal 1.
Sorry.
It would equal 1. Like the whole thing.
But wouldn't quite equal 1,
So wouldn't
right?
the exponent be 0?
Mu would equal mu naught, right? So then you would recover Newtonian fluid. Right. So if n equals 1, that's a Newtonian fluid. Right, so all of these models that we'll look at, if you plug in a particular value for a constant, usually it's going to be n, you will recover Newtonian fluids. And I think I mentioned this here. This is a model. Models are empirical, in that they're based on experiments. The values of the constants that you get out are based, again, on experiments. For each fluid, you would do an experiment and arrive at these constants. Again, you wouldn't do that in this class, but that's how these constants are obtained. As I mentioned, there are a couple of things to keep in mind about the Kerr model in terms of its limits. It has 2 Newtonian limits. I call it Newtonian limits because what's going to happen is that the viscosity is going to equal some constant. So mu equals mu naught for 2 lambda tau. So vanishingly small 2 lambda tau. And if you have a very large rate of strain, mu will also equal some constant, which is equal to mu infinity. And we have a couple of other models to discuss. The other one is the power law model. As the name suggests, mu is a function of tau, or a function of the rate of strain tensor, and the relationship is given by this formula here. Here m is a constant, and n, as before, is also a constant. And we have, for n less than 1, we have shear thinning behavior. For n greater than 1, we have shear thickening behavior. And for n equals 1, we have a Newtonian fluid. Right, because if n is less than 1, as the rate of strain increases, mu is expected to decrease the viscosity. The shear viscosity decreases with increase in rate of strain. And if n is greater than 0, as you have an increase in the rate of strain, you have an increase in the viscosity. And if n equals 1, the term in the bracket just vanishes. It's equal to 1, and so mu is then a constant, which is equal to n. Okay, and then we have the third type of generalized Newtonian fluid, which is known as a Bingham fluid. This is also the Bingham model or Bingham fluid, and an example of this is paint. And the way a Bingham fluid operates is that it is essentially a solid, and it's essentially a solid below a certain shear stress. And we'll call that shear stress tau naught. And above a certain shear stress, it operates as a liquid. So above tau naught. So tau naught is also known as the yield stress because above tau naught, you have liquid behavior of this Bingham fluid. So also known as the yield stress. And so the way we can represent this mathematically is by mu equals infinity for t less than t naught, and mu naught plus tau naught over 2 tau, 2 times the rate of strain tensor for t greater than equal to tau naught. So if mu equals infinity, right? It basically implies that it's a solid, and solids don't flow. But if it's above a certain yield stress, it behaves like a fluid in which the viscosity of the fluid is a function of the rate of strain. And so here we don't have n like we had in the previous two models. So what do you think is the Newtonian limit here? When would you approach the Newtonian limit? I'm sorry. Yeah, but if the yield stress is equal to 0, that's not really meaningful, right? There's no motion. If there's no stress applied, there's no motion. It's when the rate of strains are really high, right? So if if the denominator here approaches infinity, right, you have mu equals mu naught, right? And so the Newtonian limit here is when you have 2 mu naught times the rate of strain is very much greater than tau naught. So it's very high, very much higher than the yield stress. And at this point, you can get a Newtonian fluid. And so what I want to do here is to, real quick, just talk about the governing. So we talked about Navier-Stokes equation, which is the governing equation for Newtonian fluids, right? So we need a similar type of equation that we can use as the governing equation for generalized Newtonian fluids, right? So the governing equation for generalized Newtonian fluids. So we start with the Cauchy momentum balance, or the Cauchy momentum equation. Not Navier-Stokes. And so when you start with the Cauchy momentum balance and plug in the equation, and so just as a reminder, tau equals 2 mu times the rate of strain tensor, right? And we know that this is 1/2 grad V plus grad V exposed. Yes.
In Cardio model, what is the physical representation of n? What does n mean? The Cardio model.
N is just a constant. It's an empirically determined constant.
Yeah, so for power law model, the n is like the behavior of the shear thickening or shear thinning. For the last one, the Bingham model, it represents the yield stress, the tau zero.
Right.
But in n, it's how I can say this liquid or this material has like a 0.2 and value 0.2 or 0.6.
It's empirically determined. So I mean, it's through experiments and plotting various intercepts and stuff. There's no physical meaning to it. It's just those experimentally determined values. So the underlying basis for the model is basically they collected a whole bunch of data and then attempted to fit the data that they got into some mathematical form that can be used to generally describe any fluid that follows that behavior. So again, this is an empirical model, not a mathematically. So unfortunately, in this case, there's no underlying physical basis for what n means. It's just a constant that is a consequence of how the empirical model was constructed. So you can't determine n from first principles, essentially. It has to be experimentally determined. Okay, so tau equals, this is the most general form in which we've neglected dilational terms. And when we go ahead and take the divergence of the stress tensor, we have in the most general form this expression, right? We can only pull out mu if it's constant. For generalized Newtonian fluids, it's not constant. And so the Cauchy momentum balance, when we plug this into the Cauchy momentum balance, we have rho g minus grad p plus del dot mu, function of the rate of strain, grad v plus grad v transpose. And you would obtain an, you would obtain an expression for mu from any of the empirical model empirical models that we just talked about. Okay, we'll go ahead and end lecture here. I'll stick around for a few minutes if anyone has questions. Next week, we'll start applying the Navier-Stokes equation to look at various types of flows, some of which may be hopefully familiar to you, others may be new to you. We'll start discussing fluid mechanics and interfaces. I'll stick around for a few minutes if anyone has questions. I also have office hours at 1 today, so you can feel free to stop by on Zoom then.
That's wrong.
I don't
know why I just feel like I know. Yeah.
Where, well, like,
I almost went one time. I put my tickets in the line. Hey man, you want to buy these? $20. A little bit. Yes. Interviews? Oh, nice.
well, it's the one on one. Yeah, that's lovely.
I'm gonna work on heat transfer right now.
Oh, yeah.
You wanna work on heat transfer, or are you going home?
Yeah, I'm gonna work after my
Is there question? Interviews?
yeah, and then at 2:30 I got not that I got the still signing. And then after that I can go.
Nice, long day.
Yeah, really long. Yeah.
You do that, everybody, I think, your work we're doing is, well, so,
Oh wait.
yeah, that would be great.
I see.
That's what I saw.
But this is easier.
You guys are here. That's right.
That's it for us.
So, we like online. And you buy what is
Yeah, we haven't.
right? Yeah.
Yeah, it's just one last thing.
Cool.
Go with that.
And also the TL. Oh, I'm so dumb. And then the HC too. Oh, yeah. I just dropped it.
Sure.
Yeah.
Yeah.
Will is not necessarily. I think I literally just was sitting there, I was like, oh, this is hanging, I can't. We got it. At 11:30. One more year. Oh, I watched the whole thing, I'll tell you, it's so good.
With 202.
The last 40 minutes, because it's awesome.
This was Tuesday's lecture.
So. Yeah. What part of the thing is generalizable? It sounds like the math part, right? So like part where you reuse computation for another part. Is that the part that's generalizable? That was my takeaway. He was like, you can divide it by picking smart points, and then by reading how you do it, you can like reuse computation.
I understood that, like, similar to what you just said, at each level, you're doing n computations that solves the problem for 2 endpoints. That's why I talk about 2 for 1. So you can get a 2 for 1 at each level. So solve for endpoints, but those endpoints are also the y values for 2n x values. It's pretty abstract.
Take it off. Shelf. Yes, shelf. This is the first one, right? Just they're one from there. I thought it didn't bother. I think we recorded them all. Oh, they recorded.
There's no audio?
Yeah. If they didn't turn the mic on. Professors on Tuesdays. Now when they have audio on it. I'm not sure. Hopefully it doesn't seem like it's useful. The sessions or wow. What about the yesterday we asked them I just got there we go.